This is Formal Lab 2, and we are experimenting with Plato circuits. So for our introduction, the main goal of this experiment was to construct a circuit using an LED bulb, an electric motor, and a Plato resistor in a way so that each component in the circuit works. Our group needed to determine where to put each component of that circuit so that it would work. And our results showed that the circuit was designed that was able to make all components work as shown in our experimental design slide, and the voltage between each component did not equal the voltage of the battery. And this shows that in parallel circuits, the voltage should be equal while the current should change. But even though the circuit worked, each component should have had a 3 volts, but that was not the case. Our models show that we have our circuit diagram over to the right, and then we have our power box down to the lower left, and then at the top is our cylinder that represents our Plato model of how we determine resistivity.
So for our experimental design, we had a parallel circuit that consisted of two batteries, a Plato resistor, an LED bulb, a resistor of 1.8 ohms, and a fan motor. Everything that I just listed was in parallel with each other except for the resistor and the fan itself. Those two were actually in series, and those are labeled 3 and 4. So once we went ahead and set up our circuit like this with the exact 1.8 ohm resistor, we saw that the LED bulb was able to light up rather than if we didn't go ahead and add a resistor. And we think that's because since there's a high resistance in that area of the circuit, that means less current is going to flow through 3 and 4, and instead it's going to flow through the path that's labeled as 2. So like I said, once we went ahead and added that resistor, that's when we saw the LED to actually light up. And after we got it to light up, we went ahead and used a voltmeter and an ammeter to take the voltage and current readings from these positions labeled on this figure.
There were a few sources of error that could have occurred in the lab, but the ones with the largest effect on the measurement of resistivity were Plato sitting out, where it could have been caused an increase in resistivity and less current, and the effect from using new solar leads, which can cause a decrease in resistivity and increase in current. Now, allowing the solar leads to be used for an extended period of time versus replacing them resulted in the greatest effect on resistivity outcome. Although both sources of error could have been prevalent in the lab, we tried limiting and reducing these sources by not allowing the Plato to sit out for a very long time and using new solar leads when taking measurements. However, the data still could have been skewed. In terms of calculations, we had to use the Plato geometric dimensions as well as the circuit measurements to calculate and determine resistivity value. So from the Plato dimensions, we were able to find the length, radius, and therefore calculate the surface area. Now the resistivity equation also called for the resistance, which we were able to find through the circuit measurements. We found the voltage across the Plato and the current through the Plato, and using Ohm's law, we were able to find the resistance value of 593.9 ohms. And so we were able to take resistivity equation and manipulate it to find the resistivity value P, which was 4.7 ohms by meter. Here's an illustration of the table of recorded data and calculated data from the lab, where we had to determine geometrical dimensions of the Plato and the circuit measurements to determine resistivity.
As we saw with a parallel circuit, the current, which is the flow of charges, actually travels from the batteries and flows into the different resistors that we have in our parallel circuit. So the first thing that comes into contact with is the Plato, then the LED bulb, and then the resistor, and then the fan itself. So because our circuit was actually parallel, we can theoretically expect the following calculation or equation to hold, which is the voltage of the battery is equal to the sum of the voltage within each loop. So each loop would consist of either the current running through the Plato or running through the light or running through the resistor plus the motor itself, okay? So as we can kind of see from our calculations, that doesn't necessarily hold, and that kind of relates back to our sources of error slide, where an example of a possible error could be the batteries, since they might not have exactly 1.5 voltage, coming out of them and running through our circuit. And that could possibly cause an error in our calculations since we assume that it's 1.5, but like I said, it's not, it might not be the case for every single battery.
In conclusion, we were able to design the circuit and meet the requirements of making the motor and LED light up with the Plato resistor in our circuit. We were able to also calculate the resistivity value from our Plato dimensions and circuit measurements while considering sources of error throughout the experiment.